So yeah, this is me. By way of introduction, I guess I earned my big data stripes not really in engineering. I have some background in engineering, but I'm an experimental particle physicist by training. And in those experiments, so you take these beams of elementary particles, whether they're electrons, positrons, protons, et cetera, and you accelerate them to very high energies and collide them. And when they collide, they generate these very large high energy collisions, and you try to detect as much as you can about that event. And that'll be a megabyte, let's say, 2 megabytes, something like that. It's on that order of magnitude. But you're looking for needles in haystacks. You're looking for really rare events. So we try to collect those as fast as we possibly can. You know, if we can build the electronics to do it every 25 nanoseconds, we will. And that ends up to collecting lots and lots and lots and lots of data. So in that field, we had developed all these strategies for data collection, calibration, manipulation, analysis. We were doing all this stuff with batch computing systems, and all the grad students, all the poor grad students, spent all their time bookkeeping and resubmitting jobs that failed and worrying about which sets of calibrations were applied and this, that, and the other thing. And it was, well, fun for someone who was interested in the software side of things to design more and more efficient systems. But it left me with a real desire to build something that was A, as bulletproof as I could make it, and B, could recover from all sorts of Byzantine weird scenarios, especially in the realm of data replication. Because one of the things we did for technical or political reasons was keep copies of data sets in different facilities and universities to allow people to have like local compute clusters. So we had multi-master MySQL replications across the US, and I think I was in charge of one for a while, and grew tired of shipping bin logs around, and really wanted to do something different. And so when my colleague in that group talked about, hey, let's go pitch Paul Graham with an idea to build a new database, I was like, yeah, sure, it's worth a shot. And so here I am today. I got into Erlang by way of CouchDB because I kind of knew what I wanted to build, and I looked around. This was mid-2008, and CouchDB's little blurb on the website described all the things that I was looking for. I was like, yeah, this guy gets it. This is what I want to do. And saw that the clustering was like on the roadmap. And I said, I want to take a shot at that. And so I worked with our company. I led the effort to develop a clustering layer based on distributed Erlang that we called BigCouch. And the company's business model is one of a managed hosting platform as a service provider. We take software that's based on BigCouch and run people's databases for them. So a little bit more about that. BigCouch, we call it a marriage of Apache CouchDB and Amazon's Dynamo, right? I mean, there are a lot of systems out here that are based on the fundamental principles that you talk about: consistent hashing, quorums for reads and writes to minimize latencies and survive transient node failures. Some anti-entry mechanisms to deal with more permanent node losses or situations where you didn't write the data that you wanted to write where you wanted to write it at the time that you wanted to write it. And I felt that it was really a natural fit for the core technology that already existed in CouchDB. Right? So CouchDB is this RESTful document store. It's HTTP and JSON. Every document that you put into that database has a hash history associated with it that lets it track divergent edit histories that might happen if you were editing a document on your local machine and someone else was editing on the server. Couch has the data structures in place to track not only that those two edits happened, but it can track if one was an ancestor of another, if they were two different edit branches, and if so, where they diverged, and allow you, as the client, to ultimately employ some application-specific conflict resolution strategy to take care of that. So with BigCouch, what we did was try to leverage as much of that existing core technology in CouchDB as possible to build a system that was horizontally scalable across clusters of machines connected via distributed Erlang links. So it's fundamentally master-master because you have those hash histories to track what's going on. You don't have a situation where you need to elect a master and have writes start there and flow elsewhere. And it's certainly capable of storing redundant copies of information. In fact, it's the only way we run our systems at Cloudant to ensure that, data safety, servers die, and it should be able to restore that replica level as they come back online or as you replace them. All the buzzwords, no single points of failure, durability, fault tolerance, et cetera, et cetera. This talk is not really about this per se, but it is, all of my experience of working with Erlang over the past several years has all been, working towards this product. And globally distributed. This is not so much a feature of BigCouch as it is the Cloudant platform, where we have BigCouch clusters kind of distributed throughout the globe, sometimes spanning multiple data centers. We allow our users to kind of leverage that as best we can. But what I'm talking about here, so I called it Erlang Writ Large, and what I wanted to do was a couple of things. But first and foremost, I wanted to just kind of take a step back and think about how the principles of a good Erlang OTP application, and I'll enumerate them, are really oftentimes shared with the principles behind building a distributed data store, a big web service, big networked computing environment. And I think sometimes it's something that started in the network environment, and Erlang has borrowed that same kind of philosophy, and sometimes it flows in the other direction. And for the rest of the talk, I wanted to dig deep into high throughput distributed Erlang. We've learned a lot about it, and I think it's something that many people, I think there are a lot of Erlangers out there who don't use a lot of distributed Erlang. And I think it's really great. I think we've been impressed with how far we've been able to push that protocol, and instead of having to rely on another out-of-band method for distributing data across our clusters. But it does take a little bit of work sometimes and a little bit of tuning. And there are certainly pitfalls out there. And just generally share some war stories about the experiences that we've had operating our systems in production over the past several years. So the first principle is immutability, right? We talked about this in the video in the keynote this morning. Single assignment and all of that, which seems odd if you're coming from another language. And personally, after years of working in Erlang, I have a hard time imagining it any other way. We solved a bug in some of our web stack at one point last week. It's a Python Django app or something like this, and it all related back to a mutable global array of load balancers. And it's like, that explains it. I think immutability keeps simple bugs simple. If you have something you don't expect, the single assignment oftentimes protects you. It throws a bad match before things get really weird, and you find out down the line that your data structure is just not at all what you expected it to be. And on a performance perspective, there are a lot of nice attributes that you get in today's multi-core, many-core, high concurrency environment when you don't have to worry as much about lock contention, whether that's in memory or on disk, because you're not worried about mutable data structures and mutable memory. So it makes concurrency easy. And the same is really true when you start looking at CouchDB. And for those of you who aren't familiar with CouchDB, one of the kind of core pieces of the design is everything's based on append-only B trees. So the way those work is you have your tree structure, and you go to update a leaf. You update a value, you add a new value somewhere in that tree. You end up rewriting the path to the root, appending those nodes to the end of the file. And so all of the pointers always point backwards into the file. When you go to read the B tree, you find the header, the root of the B tree at the end of the file, and it all has back pointers to the current version of the data, right? And so it means that there's some garbage, and that needs to be cleaned up periodically. But I think it goes a long way towards creating this perfect ideal that we have like a bulletproof storage system. It becomes much harder to break if you know that you don't have to do some sort of repair mechanism after a crash or something like that. We know we've done it. If you crash midway through updating the tree, it's no big deal, because the next time it opens, it's going to go to the end of the file, walk backwards till it finds a valid header, and use it. And it'll just ignore all that in-place stuff that happens. You don't have a corrupt file. You just have some data that you didn't write, and hopefully you wrote it on one of your other copies in your clustered environment. And by the way, please interrupt me if I'm going too fast or making assumptions about the audience that I shouldn't be making. I'm happy to delve into these topics in more detail. But so immutability, I think it's a huge part of what makes our service operable by a staff of a startup operations team, as it scales to hundreds of servers. It's something that we borrowed from Erlang in a sense, right? It's a nice marriage of the way Erlang expects you to program and the way these systems are designed to operate on disk. So the second bit is supervision. And I think here I would almost take about it from the flip side. When you're building a big networked environment with lots of servers, possibly multiple data centers, you're forced into treating these things as isolated units with their own failure modes and supervising them and restarting them or building new ones as needed, right? So you've got your process monitoring tree in the operating system that restarts a daemon if it fails. And you've got, in our case with a web service, you've got proxy servers that are checking the health of the backends and knocking them out if they fail. And above that, I don't know, maybe you've got, DNS managing multiple data centers and failing over, if it detects that one of those goes offline. Whatever the case may be, is this natural tree of isolated units, with their own failure modes. And that's, forced upon you by the physical reality of the system you're working with. And Erlang forces you on that by just the very nature of how the programming language in the virtual machine is designed. I mean, certainly we can build things in other paradigms in other languages, but Erlang encourages us into this same sort of isolated faults and error handling that, that people often claim is a competitive advantage for Erlang servers. And so I just think, again, it just speaks to kind of the duality of Erlang applications inside a virtual machine and larger networks. That's all I wanted to say about that. I just think it's a nice parallel. And the rest of the time I'd like to talk about is about distributed Erlang. So just very briefly, the Erlang distribution, if you set it up just normally, is going to make a TCP connection between every node, right? It's a pairwise connection, so you have, n squared minus n TCP connections between all the nodes in your cluster. It's a fully connected mesh. And it's just one TCP connection used for all communication between each pair. I'm sure there are ways to hack around that, but that's the normal way that it works. And so I think most people's introduction to distributed Erlang, well, that's kind of small, is the RPC call, right? So there's an RPC module in Erlang, and you can say RPC call with a node, a module, a function, and some arguments, right? And that's all well and good. It's a nice abstraction. It makes you think it kind of looks like it's still sort of a local thing when the results come back to you. You don't have to think too hard about it. Unfortunately, it has some weirder properties sometimes. So the way it's actually implemented, if you go and you read the OTP source code, is that there's a named gen server living on every node in your distributed Erlang ring called Rex, right? And so when you do an RPC call, what that actually does is a gen server call to Rex on that other remote node, right, with the module function args and an infinite timeout, let's say. And if you dig in, the Rex server loop, the call handler for that message is this handle call call thing, which does a few smart things, right? It doesn't block the server to do the job that you wanted it to do. It spawns a local process to get the work done, right? So that's all well and good. And so this is the process that spawned right here. It does some cleanup of exit statuses and that sort of thing. But then when the process that spawned is done, it sends a message back to this local RPC server with the reply that it expects the RPC server to send back to you when you made that call, right? So you can picture the line of communication. It's your client process on node A talking to Rex on node B. Rex on node B spawns a little worker. Worker talks back to Rex. Rex talks back to you. Okay? And yeah, this is just Rex talking back to you. So Rex receives this reply, finds out who the original caller was, and does a gen server reply, which is really just, it's like the bang operator. It's a regular old Erlang send back to you. So that's how that works. And it's fine when everything works well, but when things aren't working well, it gets interesting. So in Erlang, if you are trying to send a message to an overloaded process, or you're trying to communicate with an overloaded port or an unresponsive node, the virtual machine responds to that condition by suspending you, by blocking your execution for some period of time and hoping that the other side that you're trying to communicate with deals with its overload situation after you're suspended. That becomes problematic because, if you remember, it was Rex that's responsible for sending communications, sending messages back to all these original client processes. You have one process on your Erlang node responsible for the remote communication with all the other nodes in your cluster. And let's say one of those nodes dies, and you've got this high throughput thing with Rex pumping out messages to all these other nodes. It's going to get blocked eventually, trying to communicate over the socket with the node that is dying, that's overloaded or unresponsive, right? So let's say node A just drops off the face of the earth, right? It's going to take a while for the VM to notice that node is gone. Meanwhile, node B is feverishly trying to send messages back to node A for the jobs that were started, and eventually it gets blocked. And not just blocked for communicating with node B, which would be sensible, right? But blocked from communicating with C, D, E, F, and G. They're all backed up waiting for Rex to get on with it and figure out how to send things to node A, even though node A is down. Sorry. It does, and there's a thing in net kernel that will detect that. So there's two conditions, right? You could just have an overloaded socket, right? Where maybe your TCP link is just not fat enough to handle the traffic you're trying to push through it, right? And there's not much you can do about that. If the socket really, if the node really does go unresponsive and the other end is just going to disconnect, yes, the Erlang VM will notice that, but it's several seconds before it actually disconnects from you. Right? And it's configurable, but I mean, it's a trade-off, right? If you set the timeout really short, you're going to get these spurious kind of disconnects all the time. So, if you're running a system that expects to respond, maybe it's powering a live website, and you need to respond in a couple hundred milliseconds before your users start complaining, that's no good. Yeah. So any overloaded or unresponsive node can suspend all those RPC communications if you're relying on this paradigm for communicating with remote machines in your cluster. And by default, that's the way the RPC call mechanism works. So you can think about ways to work around it, right? I mean, you might think, well, I'll just talk directly to my registered gen server that's not Rex. And it's like, well, OK, fine. Now it's not all communications. It's just that server. Hopefully that server is not a critical functioning piece of your infrastructure because it will get blocked if it's trying to respond to calls. So this can be problematic, but I think there are good workarounds. So what we've done at Cloudant is a couple of things. If you remember, the way that it worked was Rex would spawn the local process, and the local process would communicate back with Rex. It doesn't have to be that way. The local process, the local worker, can just as easily do a direct return back to the original caller, right? So that's step one that we did, is we wrote a new server that changed that one piece of the paradigm. So when you asked for a little RPC thing to be executed, the worker would actually receive the information when the process was initialized about who the original caller was on the remote node, and it would take care of responding directly, right? And so yeah, if node A drops off the face of the earth, all the workers that were doing jobs on behalf of node A are still going to get suspended trying to communicate with it until it comes back or not. But those workers are cheap, right? We spawned it just to do this one job and then die. It's not as if there's lots of other work waiting for this to be done, right? So you can get yourself into trouble if it really is just never coming back and getting completely overloaded. I mean, there is a finite number of processes that you can spawn in an Erlang virtual machine, but it's large, right? I mean, 1 million's not that big of a deal. So it buys you time, and it prevents one node's failure from affecting your entire cluster. It's just that link that fails. And the other thing we can do, if you really, really, really have to send a message to a remote machine from, one of your more important gen server processes in your application, you can do a non-blocking send. Right? You can try to send the message, but you can add these options if you dig into the Erlang documentation. The bang operator is just Erlang send without any options. But you can add these options to say, if the node's not connected, don't try to connect. Or if you're going to suspend me in order to send this message, don't send the message. I really don't want that, right? And then you have to check the response of that function call, and it'll tell you, no, I couldn't do it because you'd have to connect, or no, I couldn't do it because I was going to suspend you. And then it's up to you to decide what action to take. Maybe you just drop it. Maybe it wasn't that important after all. You've got other workers doing the same thing. Maybe you spawn a local process to handle sending the message on your behalf, something like that. And so we encapsulated some of that in a library that we use, in lieu of ever using Rex for anything other than like debugging and inspection of running machines in a cluster. So that was something that we learned through trial and error when we were first kind of doing serious load testing of the software about a couple of years ago, and it proved to be, a fruitful endeavor. So moving on, there's a lot you can do to monitor the health and start to change the behavior of the distribution if you know where to look. There's, in the Erlang module, there's a function that will tell you exactly the ports that are being used, the sockets that are being used to communicate with the other nodes. So you do this system info disk control, and it'll give you this, this key value list of nodes and ports that are used for the communication. And now you can go wild, right? These are regular old, like effectively ports, right? They're like Gen TCP sockets, and you can do all of the old INET communication stuff with them, right? So you can inspect, their buffers. You can inspect, I've never tried it, but you could probably turn on Nagel's algorithm or turn off Nagel's algorithm if you really wanted to, to try to tune the performance of an Erlang distributed Erlang networking stack. So once you have these ports, you can start to do lots of stuff. One of the things you can do is get all kinds of detailed statistics on the port. And so you ask, get stat on the port, and it'll give you all these counters and some measurements of packet sizes and all that sort of stuff. And it even starts to give you some undocumented things, like the number of pending octets waiting to be sent out that socket, right? And so this is clearly, a danger zone. If that value is not 0, it means processes are being suspended trying to talk over this socket, right? So like hook up your monitoring infrastructure to watch the value of this thing and, start raising alarms if it stays non-zero for any appreciable length of time because it's not healthy. And so we saw this once. And we saw it specifically over one of these BigCouch clusters that we had that was spanning a couple of data centers that were nowhere near each other. Very high bandwidth link, like 20 gigabits of connectivity between them, but we're talking about like 40 milliseconds RTT between the two data centers. So, it's not the situation that Erlang is necessarily tuned for. And you'd hope that Linux would auto-tune its way out of this, right? But for whatever reason, it kind of wasn't doing the best job. So maybe I should take a step back because that might not be obvious to anyone. If you have a fat, long link like that, right, like a satellite connection, or just a very high bandwidth link between two very data centers that are very far apart, you have a few things that you can do to try to maximize the performance of TCP over that kind of connection. One of the things you can do is, if you control the network, you can bump up the size of an Ethernet frame. Right? Instead of the default 1,500 bytes, you can try to turn on jumbo frames and reduce the number of packets that you need to transmit a certain amount of data. That could be fruitful. After that, it's a lot of buffer tuning. You try to figure out how, you try to keep the link full the whole time. Right? You try to be able to send as much data as you can without having to block and wait for an acknowledgement, from the other side. And people disagree about like the exact right way to do it. I think it's kind of a trial and error, network by network sort of thing. Linux tries to do a very good job and generally does a pretty decent job of tuning the buffers, with a little bit of setting of kernel parameters and stuff to provide okay operation over these long links. But in this particular case, we were finding that it really just wasn't doing it. So this is this plot I was talking to you about, the send pend value over time. And what we were seeing was, and we still don't actually know exactly why, but some customer at one point had a job that once a day on one of our clusters would just try to kill it, right? Would just, the amount of data transferred would climb by 50 or 60x, right? It was as if they were trying to read every document in the database all at once. And one of our nodes in the remote facility where we had a minority of nodes for disaster recovery in this other data center just couldn't quite keep up. And so it was trying to send packets back, to the primary data center where the client was, and failing, and its buffers were filling up one by one by one, and you'd go through sort of the TCP stack in the kernel, and then the Erlang VMs built-in buffers, that decide how long to wait before they start suspending you, and then you'd get up into application logic that I was talking about with Rexy. And so gradually, you'd have more and more processes backed up, more and more memory, until the node would just not do well. And so, we tried to kind of do the nice thing and auto-tune it away as much as we could, and eventually we just said, well, you know what? We have the socket, right? We can just start choosing these buffers ourselves. And so we just cranked up all the buffers, that were associated with that link. So we just kind of looped over all of the control sockets there, and started raising the buffers until we were able to get to a position where it seemed like it was healthy. And it took, it wasn't crazy. It was like 32 megs. Something like this, which was larger than you would calculate for that given latency and bandwidth of the link, but it wasn't insane. And the performance difference was remarkable. So I was really happy about this. Right? I was happy to see that distributed Erlang, which was really only ever recommended to run over local area networks, could do a fine job of utilizing these other networking environments to build a cluster that could survive the loss of a data center without losing data. It was, I forget what the exact numbers were. They were like 800 megabits per second. So close to the line rate of sending Erlang terms. At which point you might say, well, why aren't you just using another protocol to send the data? But it was a nice fit, and it made sense for our application at the time. And it was good for us to see that it was possible to take the Erlang virtual machine and extract this kind of performance out of it. Well, 25 minutes after. So that's most of what I have. Mahesh.
This is kind of the exact opposite of what you said last week.
The exact opposite.
Wide area networks, distributed Erlang, so on and so forth. Was that I didn't know and now I know kind of thing?
Yes. This was us. This was the choice of providers and networks and clients asking us to do things that we hadn't done in the past, and seeing if the system, proving that the system could do it. So I mean, I would still, of course, not recommend running distributed Erlang over the public internet, right? This was a case where the customer had multiple data centers and secure links between them and everything, right? And it was just a matter of whether we could make TCP, and distributed Erlang behave nicely over it. But yeah, of course, we still appeal to HTTP anytime we're talking about like public network or really unreliable links. This was a good network, just a long path. Yeah. Jay.
How big did you get your distributed Erlang node size?
The number of nodes in the cluster? We did a 100-node test on EC2. The bill runs up quick, right? I mean, we made it work. We built a database. We built some views. We did some search indexes and like got results. But we haven't been asked to do more than 25 nodes in production at this point. So that's like the actual production size that we've reached.
The heartbeats kill you at some point?
Yeah, at some point. At some point they would. I mean, I can't remember if I tuned the net kernel tick time at all at that point with the 100-node cluster. But I think our traffic was still dominating over the actual Erlang, Not so much, yeah. I mean, that's the thing. Like, we built these systems to more or less not care if the link is up or not, right? With things like Rexy. So if it goes away and comes back, like, we ran on EC2 for long enough that we had built things to basically expect that, right?
I guess at that point, you turn the net tick time away.
It's not that important at that point for us, yeah. I mean, it's only important in the sense that the longer you go where you think a node is connected and it's not, you'll still continue to fill up those buffers and you'll still continue to have like processes trying to use them. Whereas, once it does that disconnect, everybody just dies, right? They're just like, okay, well, that's hopeless, So I wouldn't tune it too high. Yeah.
If you were designing the distribution
Mm-hmm.
from scratch, what would you do differently?
The Erlang distribution from scratch? That's a good question. That's actually above my pay grade because I don't spend that much time in the in the net kernel stack. I would go find I see a couple guys from Ericsson around here and ask them what where it really falls down.
I would think localizing clusters as a fundamental concept in distributed.
You mean not forcing fully connected meshes, but being able to have finer-grained control over the topology and routing tables, so to speak, for the nodes in your cluster?
Suggested standards besides fully connected, rather than.
It'd be a nice feature for sure. Yeah. There's connect all false and there's groups that you can build, right? But it's I've never done it. Like I said, we're talking about 20, 30 node clusters at tops in our production systems at this point. I mean, you can put a lot of data on that, at least for the types of applications that we're generally serving. So it's been okay for us.
Has there been a change in the usage of Cloudant and
Yeah.
over time? Is it because of the customers?
Yeah.
Or because of the product?
Change in the usage. I mean, yeah. So I think I might have had a backup slide about sort of the verticals that we're finding, traction in big data. Yeah, I mean, as we've learned more about the system and as we've become, more adept at extracting performance out of it, I mean, we've been able to, enter some markets that previously CouchDB would have kept us out of, right? I mean, we've started to be able to tackle lower latency requirements than we had in the past. But I think what we find is we do have, I think there's a compelling value proposition for having the people who build it run it for you, right? Because we generally catch things before they become big problems and can fix them fast. So I think we end up with a situation where there are a lot of companies who are kind of willing to pay for that peace of mind, right? To go beyond having a support contract and to really just say, okay, look, it's your problem, So we do a lot of that where it's not just like the multi-tenant sign up for yourself customers, but it becomes more of like a database that really deserves its own cluster, but one that they're still just working with us to have us manage.
I was thinking more along the lines of application types. Like when
Mhm.
you were MapReduce, you were always dominated by I/O in terms of MapReduce, but you were moving towards a solution where you'd have dedicated CPUs.
That became unnecessary because Intel got fast. Like, we moved off EC2. You know, we still have a presence on EC2, but it's mostly for providing like Heroku platform as a service stuff. But I mean, when you can get, you know, dual CPU, 10-core machines, like, you don't need to dedicate servers for CPUs. You just kind of trust Erlang to scale right up with you, and for the most part, it does. You know, so when we were able to actually choose the right hardware for the job, that you know, it improved our capabilities a good bit. No, I mean, I'd like to see, you know, going forward is definitely more applications that leverage the replication in interesting ways, right? Because I think it's, you know, if you have an application that needs it, like there are relatively few data stores around that can, you know, that have that kind of capability built into the core. So like you know, we do have some like mobile applications, for instance, where they'll have a local data store synchronizing with, you know, a cloud database. And I think that's, you know, a place where I'd like to see future development for sure. I mean, I don't know. Tying it back, you know, big data means so many things to so many different people, right? For some people, it's all about just like, let me build the biggest to-do cluster that I can and crunch my logs as fast as possible and, you know, make it 1 cup of coffee instead of 2. But I think that, you know, it also behooves people to think about creative ways that you might reduce that data volume at the source, right? Do some processing, do some analysis, you know, before you have to like, you know, boil an ocean to get it all into one place and crunch it and never throw anything away. So fundamentally, I mean, sensor-generated data is going to grow so fast at some point that we can't possibly keep building bigger and bigger data centers to manage it all, right? We have to do smart things with it. At least that's my opinion. I don't know. Maybe the NSA has got a facility somewhere I don't know about. But, right.
How is this different from React?
There are a lot of similarities, aren't there? That's an excellent question. We have a lot of Bashonians here. Well, I think React is a little less opinionated about the data types that you put in, right? It allows you to just throw binaries in there. I haven't kept pace with all of the developments and sort of like 2i, secondary indexes, and different things that React's been adding. But one of the things you can do in this system is, you know, after the fact, after you've already got a database built, you can upload, you know, some JavaScript, MapReduce functions, or whatever to build and then maintain a secondary index on that data. I think React might require like a dump load cycle to build a new index on data that you already have in. Do you have to like read it and write it back with the headers? Yeah. So it's not that much different, but it's sort of, you know, you have to do that client side instead of having the server build that up for you from scratch. And then, you know, then there's replication. I think React's started to add things. Well, I shouldn't speak for them. I heard that they were adding things in terms of like multi-site replication, which they had in their enterprise offering, and maybe there was more of that coming in React proper to deal with, you know, the case where you've got a cluster on the East Coast and one on the West Coast, and you want to keep them somehow synchronized. CouchDB has, you know, had primitives for that for a long time. But yeah, I mean, there's a lot of common philosophy there. You know, I think the real difference in many ways is in the business model. Like, almost all of what we do is, you know, like our company makes a living by managing the software that we write. You know, controlling the servers and providing it as a service to people.
So I use both, and CouchDB is definitely much easier to use than React.
If you're in the single server, I have no doubt. You know, it's sort of like a smaller piece of kit, right? When you get like when you're building big distributed systems, it's always a challenge to make it simple. You know? Yeah.
Couchbase is a similar kind of application. So what's your take on CouchDB versus Couchbase?
Yeah, we should get a beer sometime. No, no, it's Couchbase. You know, so Couchbase was the mem-based technology, which is sort of the memcached protocol.
Yeah.
right? And merging it with Couch's storage engine. And I think at one point in time there was like a hope that they would provide most of the CouchDB interface for that. But as I understand it, these days it's much more use your existing mem-based memcached interface, but now we've got Couch's like bulletproof durable storage engine underneath instead of SQLite, right? And it's a storage engine that we've tuned and written like explicitly to handle our workloads. I think that's kind of their pitch these days. But I think it's definitely tuned for key value operations, microsecond latencies as fast as possible. And it's a clustering architecture that is really geared towards kind of just working over like local reliable networks. Like it's a master-slave, I think, replication topology for dealing with redundancy. So you don't have the kind of flexibility to reconcile edit histories if you're trying to do, the sort of thing we've got your East Coast and West Coast data centers. So I think there's, Couchbase as a product these days is much more about like memcached than it is about like the CouchDB RESTful interface.